Okay, so in problem 10, both parts asked for the magnitude of the induced EMF, which meant we just took the absolute value, which meant we disregarded any negative sign. So you may be questioning, why is there a negative sign in Faraday's law? Well, it turns out another scientist by the name of Lenz came up with an explanation. In fact, he was so successful, he got an entire law named after him just for explaining a negative sign. That's pretty cool. So you have your notes page in front of you. Let's talk about Lenz's law. Let's go ahead and read this. The induced current in a loop of wire is such that the magnetic field it creates opposes the change in flux or maintains the status quo. Well, that is just obvious. Didn't take a genius to figure that one out, right? No? Okay. Let's see what's going on here. So it's all about this idea that the universe is stubborn. The universe doesn't like change. And so when you change something, the universe tries to get it back the way it was. It's almost like a conservation law, if you want to think of it like that. So whenever some external situation occurs that causes a change in flux, the universe tries to oppose that change by creating a magnetic field, by inducing a current, or inducing a voltage to cause that to happen. So let's look at some examples. So let's take a look at this first picture here. What we're looking at here is a bar magnet moving downwards, and yes, we are going to look from the side, so we can't say it's moving down. I apologize, the end didn't show up too well here. And this is a rectangular loop of wire. So here's the near edge, here's the far edge. We're looking at it in perspective. Can you visualize that? I hope you can. So we're looking at it from the side. Here's the close edge, there's the far side. And what I like to do is I like to go through a series of steps. The initial magnetic field in the area we're looking at, the change of the magnetic field, and then the induced magnetic field. And we're going to see what happens because of that. Now, it is not technically correct. We really should be talking about a change in flux, but I always like to relate to the magnetic field because I think that's the more tangible way of looking at it, the one that most students really understand. So what first we want to do is identify the initial direction of the field at the location we're interested in. The location we're interested in is this loop of wire, which does not have a source of voltage. It's just all by itself. It's just a conducting rectangular loop. And so here's the North Pole, which is relatively close to the wire, right? And so if you're at the location of the wire, which way is the magnetic field produced by this bar magnet? Well, we know our rules. Magnetic field lines flow out of North Poles. Let's draw that, right? So here's magnetic field near the North Pole coming out of the North Pole. And so they're all generally pointing downwards, right? So we'll say our initial direction of the field location loop is downwards. And this magnet is coming closer and closer to the loop. So if you're at the location of the loop, what should you register? What should you feel about the change of magnetic field? Well, when it's far away, it's relatively weak, and as it comes closer and closer, that field gets stronger. So we say the change in the field you record is down as well. If that's bothering you, think about in terms of velocity, right? If an object is moving down and getting faster, its change of velocity is down as well. So here it's like we're adding extra field because the magnet's getting closer and closer, and that causes a change in flux. More and more field lines are in this location of the area of the loop. But the universe doesn't like that. It says, well, look, if you're bringing more and more field there, we don't like that. We used to have a field that pointed down, now it's too much down, so the universe is going to induce a magnetic field that opposes the change. This is going to create a magnetic field that points up to try to take away the extra field you're creating by moving the magnet towards it. How does it do that? Well, the only way to make a magnetic field is to move charges around. And so the question then is, which way are the charges going to flow to make that happen? So here's where you're going to be doing a right-hand rule. So I like to do the right-hand rule shortcut. So the wire itself is in the horizontal plane. And I want you to see, so charges moving around in a clockwise direction as seen from above, or in a counterclockwise direction to create this magnetic field that points upwards. So go ahead and try it on your own. Alright, so you should be getting in this direction a counterclockwise way, so that in this near section of the wire, the charge is moving to the right. So now if you didn't get that, now try it using the right-hand rule shortcut. So your fingers follow the charges, in this case to the right in the near section, and they flow away from you, and then to the left, and then back. And as you do this, your thumb should be pointing up. That's the field we need, right? So the universe is going to make charges move around in this direction to create this magnetic field, to oppose this change, and try to restore this original weaker magnetic field. That's the whole idea. The universe tries to maintain the status quo. Alright, let's look at another example. So same situation, we have our loop of wire, no source of voltage whatsoever. Now the magnet is sort of already in the area of the wire, and it's moving downward. So it's continuing the same general direction. We're going to go through the same steps: initial field, change in field, induced field, and finally current. But again, we need to see which way is the field originally pointing. Well, now the South Pole is near the location of the wire, and we know magnetic field lines point inwards towards the South Pole, so we'll draw some of those field lines. And that's also the initial direction of the field. If we're sitting here at the location of the loop, the magnetic field near the South Pole is pointing downwards. That's the initial direction. But we are now taking the magnet away from the loop. All right, and so as the magnet moves farther and farther away, are we registering an increase or a decrease in field? That's a decrease. That would be a delta B pointing up. Right? It was pointing down, but we're taking it away, so we're changing in the opposite direction. Again, if that bothers you, think about it in terms of velocity. If an object is moving down, but slowing down, its change of velocity is up, taking velocity away. And that's what we're doing here. By moving the magnet away, we're taking field away. But the universe says, wait a second, we used to have a field that pointed down, and now all of a sudden you're weakening it? We don't like that, so it will induce a field that points down to try to oppose the change, try to replace the field lines you are taking away. The universe is very fickle like this. Whatever you do, the universe doesn't like it, doesn't like change, it tries to restore it the way it used to be. Alright, so now you're going to do your right-hand rule shortcut and figure out which way our charge is going to flow around the loop of wire to create this induced magnetic field that points down. So hopefully this time you got it the other way, that now the charge is going to move around in a clockwise direction. If that you didn't get that, try it now. So in this near section of the wire, charge is moving to the left, so your fingers are pointing to the left, and then just curl them all the way around, and then you should see your thumb is pointing down, which is the whole point. That your thumb should point down. That's the induced magnetic field that opposes the change. So let's just put some words on this, right? So in this section, before the magnet enters the loop, there's a magnetic field pointing down. That's this, initial magnetic field. The loop wants to maintain the flux created by that field, and so it generates a current to oppose the gain, right? As you move the magnet towards it, more and more field lines are at the location of the loop, and it doesn't like that, so it creates this magnetic field to oppose it. In this situation, as the magnet leaves the loop, there used to be a field pointing down, and you're taking it away. The loop wants to maintain that flux of these field lines pointing down, so it generates a current that replaces the loss, because you're taking field lines away. It's all about maintaining the status quo, trying to get back the way it used to be. The universe does not like change. Let's look at a completely different situation. You probably don't have room on that notes page, so let's go back into your handwritten notes, and we'll look at our very familiar situation. We've seen this so many times before, so I want you to go back. I want you to recreate it one more time. Remember, we're looking down at the situation. That's really important, looking down at it. So here's our conducting rod sitting on top of these conducting rails. There's a resistor, and there's an external magnetic field produced by some large laboratory magnet pointing into the page. The length of the conducting rod is L, it's moving to the right, and here it is sometime later. So now we're going to use Lenz's law. We're going to go through the exact same steps. See if you can do it on your own first. Okay, so clearly the external field is pointing into the page, so there's no question about that. And then, what's the change in field? Well, as we move this bar over, can you see we're putting more X's in the interior of the loop? Right here we have 1, 2, 3, 4, 5, 6 X's, and now we move it over, we have 7, 8, 9. We're literally adding more field lines into the page. There's now more field lines enclosed by this whole area than there used to be, and so the change is into the page. But the universe says, wait a second, if you put X's in, we're going to try to take them away by inducing a field out of the page. Right? It's literally just opposing this. Alright, so if you didn't get this far now, go ahead and try the right-hand rule shortcut. So that we want a field that's pointing out of the page. Which way will charges flow? You better be getting counterclockwise this way. So when your finger's pointing around this direction, your thumb is pointing out of the page to oppose this change. And now, if you just go back and compare this to any of the problems you've done before, you saw it's the exact same situation. The charges were flowing to the top of the page here, or this is the positive end, and they're flowing out this way. No matter what we do, we're going to get the same results, which is great. That you can use Lenz's law for this situation, or if you don't like this, if you're confused by the whole Lenz's law, you can go right back to thinking about those individual protons inside the inside the moving conducting bar. Positive charge moving to the right inside a field into the page will feel a magnetic force to the top of the page. The protons will collect here at the top edge. That's going to be the positive terminal, allowing charge to flow around this way. And so I'll give you a couple more steps. If that makes more sense to you, you're going to get the exact same results either way. By imagining those individual protons and how they feel a force, or doing Lenz's law, you're going to get the same results.